All right, awesome. So now that it's 7 o'clock, let's go ahead and get started. So I saw a couple of you guys have already answered our icebreaker for today, which is your favorite ice cream flavor. Okay, so I think our first answer was from Rifa Yamin, and their favorite ice cream flavor is cookies and cream. Okay, and it seems like Zia and Aries both agree with that. I think I have to agree with that too. I love cookies and cream. I think hands down, it's like the best combo ever. Nahal says cookie dough, which I feel like is along the same thread of cookies and cream. I think it's just like a slight flavor difference, but like very similar. Amari says a little complex. He would like vanilla, cherry vanilla, and rainbow sorbet, but normally prefer cherry vanilla. Okay, that's definitely very unique. I don't think I've ever had cherry vanilla ice cream before. But I totally understand where you're coming with sorbet because like lately I've been liking sorbet a lot. Like I don't know, like the dairy and the ice cream is just not sitting well with me anymore. So like sorbet is like kind of my go-to these days. But yeah, I think I'm more of a sorbet person. Anvika says vanilla, cookies and cream, chocolate and pistachio. Okay, that's a really good list. I think cookies and cream is a good combination of like vanilla and chocolate. I loved pistachio when I was a kid. Like it was hands down one of my favorite flavors. And then I kind of like grew out of it because I was like, oh, I don't like nuts that much. But yeah. Okay, but just says also cookies and cream. Awesome, awesome. But I bet he says vanilla. Cool. Yeah. Lots of cookies and cream and vanilla and chocolate, which I think is like those are all fair answers. So I'm not like super surprised yet. I think if I so I like I said, if I had a favorite ice cream flavor, it would probably be cookies and cream. But because I don't like ice cream that much, I like sorbet more. I think like I would go well, sorbet is like really nice because you can do like all kinds of fruit flavors, which is like kind of my thing. So I would go with like I don't know, like an orange sorbet or like a raspberry sorbet. I think those are really good. Um, but yeah. All right. If you haven't already, let us know what your favorite ice cream flavor is. I'm very curious. Yes, I love desserts and I love ice cream. So this is very fun for me. Or he says, I don't really like ice cream, but I eat it sometimes. Yeah, that's totally fair. Ice cream can be like, I don't know, like you have to eat it at the right time. I agree with that. Um, but yeah, I'll eat it occasionally when I'm in the right mood. I so agree. Or he says it's too sweet. Yeah, yeah, I can kind of see where you're coming from with that. I mean, it is literally just like whipped milk with a bunch of sugar. So like it is gonna be a little sweet. But yeah. All right. Amari says the sorbet is multi-situational. Yeah, I feel like sorbet is very applicable. It's literally just like what is it? It's literally just like have you guys had like Kona Ice? You guys definitely know what Kona Ice is. Yes. Okay. Perfect. Perfect. I was like, I know this is like a kid thing that when I was young, but like it's definitely it's still relevant. Okay. Good. Kona Ice is great, but I like to think of sorbet as like Kona Ice or like shaved ice. Like that's what I enjoy because I love to chew ice. That's like a random fact about me. I love chewing ice. It's very odd. So that's why I like sorbet a lot more. The texture is better. All right. Let's see. Oh, Jason says fish. That is such a unique ice cream flavor, and I really have so many questions, Jason. If you would like to elaborate, that would be great. All right. Let's see. And because says I've never tried sorbet, but it sounds pretty good. Like shaved ice. Yeah. Sorbet is really good. Like if you feel like ice cream is too heavy, like sorbet is very nice and light. So I like it like that. Yeah, shaved ice is not the best definition, but it's like the closest thing I could think of. It's like ice cream without dairy. So like that's what I think of shaved ice. But yeah, it's not exactly shaved ice. Wow, Nahal, that looks delicious and also like diabetes, but wow. I think is that like homemade? That looks homemade. Okay. Um, yeah, Kona Ice is so elementary school core. I loved Kona Ice. You get like $3 to school and then buy your favorite flavor. Like it was a whole thing. But yeah, we don't really do Kona Ice in high school. It's kind of sad. They should do it more often. Maybe I should petition for that. Oh, it's $5 now? Oh my God, that's such a scam. That is actually such a scam. It was $3 like 10 years ago. So I guess it doesn't mean much, but it was $3 when I used to have Kona Ice days. Yeah. Oh, Nahal doesn't know if that's homemade. That's okay. It looks really good, but that also looks like a lot of sugar. I don't know if I could eat all of that. Is that like banana split? I think it is. I can't tell. It looks like a banana split. Or honestly, it just looks like everything, like all the flavors in a bowl. Yeah, Anvika's right. That is inflation. That is inflation. Reese says my favorite Kona ice flavor is Tiger's Blood. That is what I never tried because I was like, what a weird name. Like, I'm not gonna try this. So wow. Yeah, I wish I tried it now, but I never had it before. Zia says, I kind of hate it because when I eat it, it's just like ice. See, Zia, that is exactly why I love it because it tastes like ice. Yeah, I don't know. I'm a big ice person for some reason. Oh, Amari's having an ice cream party at his school. That is so awesome. I wish I still had ice cream parties. I wish I had ice cream parties. That would be fun. Yeah. Oh, wow. Oh, yeah. Okay. Amari says my favorite was key lime and pina colada. I like key lime a lot. I did not like pina colada. Mostly, I just like the things that were like green. So I got like the greens and oranges and like the yellows. So very not flavorful. It was just kind of random. Um, cool. Yeah, Tiger's Blood was good. That was a very popular flavor, I know. I know kids used to like put all the flavors in sometimes. Like that was just chaos. Yeah. Today I had like this really nice like vanilla ice cream bar wrapped in a mango sorbet, and it sounds kind of weird, but it actually tastes like really good. So I thought that was like really fun. Oh, I forgot to write down everyone's favorite flavors. That's my bad. I was so like excited by the discussion. I just forgot to write your guys' stuff down. That's okay. I think we had a good talk. So on that exciting note of Tiger's Blood, let's now go tackle some geometry problems. So today we're gonna kind of breach, or not breach, kind of like, I guess, enter the foundation of geometry, which is triangles. But I want to start off with like special triangles, like specifically special right triangles, because I think this is like a good introduction to see like some cool properties of triangles, and then we'll kind of like work our way up to some more advanced kinds of things relating to triangles. So today we're going to be focusing on like special right triangles, some cool properties, and then also maybe some like ideas related to them. So we'll kind of start from there. So special right triangles are very special, but for two reasons. First, they have an angle that measures 90 degrees. That's what makes them right triangles. And second, they have some really nice like ratios going on with their sides and stuff, which is why we care about them because their ratios are very like nice and easy to work with. So the two main like special right triangles we have are the 30, 60, 90 triangles and the 45, 45, 90 triangles. So some of you guys might be like, okay, why is she just like spewing these random numbers? We'll take a look at that and we'll take a look at what these numbers represent. But let's first go ahead and look at the 45, 45, 90 right triangle. So, hmm, what do you guys think the 45 and the 45 and the 90 represent? I think I see some answers in chat, but what do you guys think it represents? Like based on what we've talked about. Oh, okay. Tanish, if you can contact me, like, or if you can stay after class, we can figure that out because I want to make sure you're on the email list because that's how we send out everything. So just stay after class and we can fix that. Okay, awesome. Yeah, okay, so Manit says, oh wait, 45, 45, 90 doesn't tell me much about what that is, Manit. Give me an extra descriptor. And Mika says they are ratios for the sides. Close, we need a little bit more than that though. You're on the like right track, but not entirely. Yeah, it's the right triangle. That's good. That's good. Yeah, and Vika says degrees, which is absolutely right. So these are degrees, and like Manit says, they're the angles of a triangle. Oh yes, okay, I see that now. Thanks, Enrica. But yeah, and a good way to see like, oh yeah, these are actually angles is if you add them all up, right? You do 45 plus 45 plus 90, that comes out to be 180. So when I say 45, 45, 90, I'm talking about the angles inside a triangle, specifically a right triangle. So we know this is a right triangle. What else do you guys notice is special about this? Do you guys see anything special? Hmm. I know you can't really get much from just the angles, but there is one other property. Yeah, that is true. All the angles do sum up to 180, but that's true for every triangle. Is there something else? Oh yeah, okay. I see a couple people saying it. Yeah, it is an isosceles right triangle. Yeah, isosceles is a hard word to spell. Honestly, I get tripped up sometimes. So the reason why we know it's isosceles is we can look at the angles. So in an isosceles triangle, you have two angles that are the same, and the sides corresponding to those angles are also the same. So you'll talk about different classifications of triangles, and isosceles is one way to classify the sides and the angles. So this is an isosceles Right triangle. If you guys like struggle with isosceles, that's okay. Like I struggle with it too. It's a hard word. So isosceles means two sides, and thus two angles are the same. Two sides are same. Two angles are same. Okay, amazing. So that means we have two equal sides. So in a right triangle, we have these things called legs, and we also have these things called a hypotenuse, which I think you guys are all familiar with, so I'm not going to spend too much time on that. So the hypotenuse, remember, is going to be derived from the legs. The hypotenuse has to be greater than the legs. That's given. So if the hypotenuse cannot equal the legs, that means the two legs themselves have to be equal. So if I draw that, that's going to look a little something like this. What do we think about that? Does that kind of make sense? Yeah, and Tanish puts in why the hypotenuse has to be greater than the legs. It's because the hypotenuse, which we can call c, just a random variable, is equal to the square root of both the legs squared. So a squared and b squared. So hold on, let me write that out like properly. So we can say that c squared is equal to a squared plus b squared. In other words, the square of the hypotenuse is equal to the sum of the square of the legs. So this is like very, very important. It's known as the Pythagorean theorem, and I think you guys have all seen and heard this before. So this is definitely very familiar. There is actually several nice proofs about this. Maybe if we have time, we'll go into it. But for now, since you guys are so acquainted with this fact, I'm just gonna leave it up here. And if you guys have questions or like, okay, where is this like random formula coming from? I've never seen this. We can discuss the derivation afterwards. But for now, this is our main thing. Okay, so like I said, let's go ahead and label the angles, right? So this is obviously a right angle, and this is our 45-degree angle, and this is our 45-degree angle. So because these two are the same, that means the sides corresponding to them are also the same. So you're like, okay, how do I determine if a side is corresponding? Well, that is a great question. A side is corresponding to the angle that it's opposite of. So in this case, this A is corresponding to this, let's see if I can write in a different color. Um, this like green angle over here, I'll make it green. So A is corresponding to the green angle, and actually I'll write A in green. And then similarly, B is corresponding to this blue angle. So we know that because these angles are the same and the sides corresponding to them also have to be the same. That means that A is equal to B. Okay, awesome. So now, can you guys find out what c squared is using the Pythagorean theorem? What is c squared? Or if you can calculate c immediately, that would be cool too. You can give me c or c squared, either one. Think about how we can substitute the values into our equation. We know that a squared is just like a squared. And we know that b is a. So this becomes c squared is equal to a squared plus a squared. So this is just 2a squared. Yeah, and I'm seeing a couple people put this in chat, so very good. And then I also see people solving directly for c. So if you're solving just for c, you take the square root of this equation. So that means c is equal to the a times square root of 2. Alrighty, let me pause here. How do we feel about this? I'm gonna go ahead and put up like a nicer diagram, but like before I do that, how do we feel about like figuring out what C is in terms of A? Good? Okay, yeah, I think a lot of you guys are familiar with like the 45, 45, 90 triangle and like its properties and stuff. But if maybe you were just like, oh yeah, 45, 45, 90 triangle, I know the ratio for that, I'm good, and you don't know like where the ratio come from, this is like a good review. Okay, let me just like recap but with like a prettier diagram because I think uh that could help a little bit. All right, so in this diagram, we can notice a couple of things. First, this reflects our 45, 45, 90 triangle. You can see that it's a right triangle and it's also isosceles. And because it's isosceles, we can say a couple of things about this side. So let's say this side, opposite the 45-degree angle, is A. Let's say this side, oh no, that's not what I wanted to do. Okay, this thing in green, this angle here in green, is going to be corresponding to this side over here that I've circled in green. because it's opposite. That's how we denote corresponding sides. That's a really important concept, being able to determine like the corresponding side to an angle. That comes up in a lot of formulas too. So that kind of notation is very, very important to remember. Okay, we also have another 45-degree angle, which is this colored blue thing over here. But we said that the side like corresponding to the 45-degree angle, it's A. So even though this angle is not the exact same one as the green one, it's the exact same value. It's the exact same measurement. So we say that it is also equal to A. That's why we have A on both of the legs of the right triangle. Does that make sense? What do you think about that? Okay, I don't see any questions, so I think we're good to move on. Now, from here, we just do a little bit of Pythagorean theorem. Like I said, we could totally prove this. I'm just not going to do it now for the sake of time. So if I went ahead and plugged in the Pythagorean theorem, I would get something like my hypotenuse squared is equal to the sum of my legs squared. So that would be a squared plus a squared. So that means my hypotenuse squared is equal to 2a squared. So my hypotenuse, which I'll just write as hyp because I'm super lazy, is just going to be a squared 2. So a times the square root of 2. Does that make sense for those of you guys that were a little bit confused? Okay, I don't see any questions, so I'm going to go ahead and move on. So we say that if you have a 45, 45, 90 triangle, the ratio of the sides is going to be 1 is to 1 is to square root 2. And that's pretty simple to see because if we look at this diagram and then we divide all the side lengths by a, we get 1, 1, and square root 2. So this is a really important property of 45, 45, 90 triangles. Their sides are in this ratio, and this comes up all the time. You honestly don't even have to memorize it because of how much you'll use it in problems. You'll like know it like the back of your hand. But yeah, this is a very important triangle, and I would recommend you understand like how we got to the fact that 1 to 1 to square root of 2 is the ratio. Okay, now that we've gone through this little thing, how do we feel? I think like most of you guys have at least encountered this ratio or at least like know what it is. So I don't think this one is like the most random one. Okay, I think we're good. All right. If you guys have questions, though, feel free to stop me. The next triangle we're going to talk about is the 30, 60, 90 triangle. I think this one, like everyone still knows the 30, 60, or most people know the 30, 60, 90 triangle, but I feel like it's not really discussed the important properties of such a triangle. So let's go ahead and take the liberty to do that now. But first, I need to clear this. I need to clear the screen so we have some space to write. Okay, lovely. All right, so I'm going to take like a couple steps back and I'm going to start with an equilateral triangle. Now you might be like, okay, Sam, you said you were going to talk about a 30, 60, 90 triangle. Why are you drawing an equilateral triangle? That has only one of the angles we talked about. Well, you will see why I'm going to draw such a triangle. Let's see. I don't think, okay, maybe this was like not ideal. It's okay. This is gonna be our fake equilateral triangle. I don't think it's actually equilateral, but it looks equilateral. Yes, okay, and Manit has literally predicted what I'm going to do. I am going to split it in half. But let's take a look. Why would I want to split it in half, right? So I know I have in an equilateral triangle, every angle is 60 degrees. Now, I want to try to construct a 30, 60, 90 triangle from this. So I have one of the angles is 60. That's good. And I know that 30 is half of 60. And I also know if I can make like something perpendicular here, that'll be 90 degrees. So what I'm going to start doing, my motivation here is to get that 90-degree angle, which I can get by dropping a perpendicular. So I'm going to start drawing my perpendicular, and if I keep on going, you'll notice that it passes through this vertex. So this is going to be my 90 degrees. And even if you didn't believe that this perpendicular line happened to bisect this angle, you could actually very easily calculate the angles, right? Because if we look at this triangle here, and I'll outline it in a different color, maybe purple. If we look at this purple triangle here, oops, okay, you will notice that it is a triangle. And because it's a triangle, the sum of the angles is obviously 180 degrees. So we know that one angle is 60 degrees and the other is 90. So if I did 180 minus 60 minus 90, this would be 30 degrees. So that's going to be this angle up here. And that's how you know that this perpendicular line that I happen to drop is also going to be an angle bisector. It bisects this angle. Someone has dropped the word an altitude, and that is absolutely correct. This red line that I've dropped is also an altitude. If you are like, oh my gosh, Sam is throwing like a bunch of random vocabulary words at me, that's okay. We will talk about a lot more of these vocabulary words later. But if you know what these are, that's good. If you don't, that's okay too. Triangles have a lot of special lines that are really important to know, and that's why we're going to talk about that in a separate class. But this is a good way to like get acquainted with some of these important lines. Okay, so now that we see that a 30, 60, 90 triangle can be constructed from half of an equilateral triangle, we can go ahead and find our side ratio. So I'm going to enlarge this diagram because it's like really small and I have a lot of space. So, alrighty. Okay, that's so much better. Wow. Okay, now that I have this gigantic picture, let's go ahead and take a look. So let's say I have a side length of 2. You might be like, okay, why not 1? Well, if I divide the side in half with this little bisector altitude type thing, this should be 1. And I don't want to deal with fractions, so that's why I'm going to let this be a whole number of 1. All right, what do you guys think about getting these two sides, the hypotenuse and the shortest leg? Good. Okay, amazing. So now we do Pythagorean theorem just a little bit different. We're going to call this side h. So we're going to say that 2 squared is equal to h squared plus 1. So that means h squared is equal to 3, meaning h is equal to the square root of 3. So I can go ahead and replace this with, oh, actually, maybe I shouldn't erase it just in case, square root of 3. Okay, so now you can see the ratio of the sides in a 30, 60, 90 triangle is 1 is to square root 3 is to 2. Okay, this is really important, and you might be like, okay, how do I know which side corresponds to which angle? Like, that's a good question. So, like I said before, in the 45, 45, 90 triangle, you can tell opposite sides correspond to different angles. So, similarly, we can do the same here. If I have the smallest angle, that's going to correspond to the smallest side. And the largest angle is going to correspond to the largest side. So in this case, I have the angle of 30. That's the smallest in this triangle, and that's going to relate to the side of length 1, which is the smallest length. But I also have this 90-degree angle, and that's the largest angle, so that's going to relate to my largest side, or the hypotenuse. So that's a good way to remember where this is coming from. Like I said, knowing how to determine like which angles relate to which sides or corresponding to each side is a really important technique, because that's something that can determine like whether you get a problem right or wrong, because you might like plug in the wrong number in a formula or something just because you did not like remember which side corresponds to the angle. Okay, how do I feel about 30, 60, 90 triangles? Is this good? I think like most of you guys are familiar with special right triangles, but I feel like sometimes you don't understand, like we don't really get taught like where do these rules come from? So that's why I think it's important to get to look at that. Okay, let's see, a couple of things. Alrighty. All right, I do see some questions. Good. Okay, cool. Ratio for the sides is 1 is to 1/2 is to square root 2 over 3. And Vika, I don't think that's correct because mostly because there shouldn't even be a square root to begin with. If you're dealing with 30, 60, 90 triangles, it's going to be a square root of 3. Sometimes you can divide it by 1/2, but I think it's easier to remember all whole numbers, or at least no fractions. So 1 is to root 3 is to 2 is how I like to remember it. Okay. Yeah, let's briefly recap. So I think it's kind of hard to like pull some of these numbers out of nowhere if we're just looking at the 30, 60, 90 triangle. So instead, let's look at an equilateral triangle, which happens to be a 30, 60, 90 triangle, just kind of like copied over, like flipped over an axis. So now that we have this, we can relate one of the sides, this hypotenuse, to this other side, which is half of this length. So this small side is 1 and this longer side is 2. And then we go ahead and use Pythagorean theorem to find the missing length, or what we call the height. And that's just going to be square root of 3 using this equation over here. So we can see that the ratio is 1 is to square root 3 is to 2. Awesome. Okay, this is really important. This comes up all the time. You will also see like triangles constructed from 30, 60, 90 triangles, like not just equilateral triangles. You'll also see like a 30, 30, 120. This isn't like a special right triangle, so I'm not going to address it, but like its properties are very similar to this because it's just like two 30, 60, 90 right triangles kind of like stuck together on the short side. Okay, cool. That was a little side tangent. If you're like, okay, that was really confusing, it's okay. Don't worry about that. All right. Let's do a quick problem on this one because I think this is like definitely a little more challenging than an isosceles right triangle. So a quick question that I will paste here so I don't have to write it out. All right. Can you guys go ahead and take a look at this problem for me? If the hypotenuse of a 30, 60, 90 triangle is 8 square root of 2, what is the leg length? Wait, I think I lied. Hmm. Okay, this is not ideal. Yeah, so this is a 45, 45, 90 question. Then yeah, the leg length is 8. That is absolutely correct. I intended this to be, I intended for this to be 30, 60, 90, but you guys got what I meant. Yeah, so if the hypotenuse is 8 root 2, and I'm looking at a 45, 45, 90 triangle, then the leg length is 8. So let me change this really quick, and let me change the problem. Let's say if the hypotenuse is 6, what's the longer leg length? So can you guys tell me what the longer leg is equal to if the hypotenuse is 6 in a 30, 60, 90 triangle? What do you think? Okay, wow, I see so many different answers. I see 4, I see 3 square root of 3, I see 9, I see 9, 3 squared 3, 3. Okay, cool. So let's take a look, right? So if the hypotenuse is 6, remember the ratio. 1 is to square root of 3 is to 2. I'm asking for the longer leg length, so that's going to be the number in the middle. Now, to get a hypotenuse of 6, I have to multiply this entire thing by 3, because remember, this 2 corresponds to the hypotenuse, so I need to make this a 6. So this will become 3 is to square root of, is to 3 root 3 is to 6. So that means my longer leg length is 3 root 3. What do we think of that? Is that good? For those of you guys who gave us like maybe 3, you guys are looking at the shorter one. But notice I asked for the longer one. Okay, perfect. I think we're good. Yay, amazing. All right, so the reason why like special triangles are really important, like no, literally no matter what geometry class you take, someone will bring up special right triangles at some point. And the reason why that is because they show up a lot in geometry, and a lot of cool stuff can be done based on special right triangles. So they show up in geometry, they show up in trigonometry, they even show up if you're looking at things like ramps and roofs and stuff. And some harder like competition math problems will look at triangles in this kind of perspective with ramps and roofs. So it's very fun. Yeah, and the ratios like make these triangles very approachable. Often, like when you enter the world of trigonometry, you'll see that like side lengths can be very, very odd compared to like angles. Like it is very rare that you have like nice angles and nice side lengths. Special right triangles are a good one. That is part of the reason I don't really like trigonometry because I think it gets very messy and stuff. But yeah, some people like adore it, which I think is great for them. Okay, so let's do a couple of practice problems and then kind of work from there. Oh, Anvika likes trig. Wow, you are a very talented person. I envy you for liking trig. Okay. Cool. So let's go ahead and take a look at this question. This one is a lot clearer. So if you guys were confused with the last few, hopefully this one is easier. Yeah, Vivon agrees with me. He's like, man, no way you find trig easy. Yeah, it is a contested topic amongst all. Yes, trigonometry is quite difficult. I mean, I even struggled with it when I took it. It was definitely a little difficult. Um, Honestly, like unless you're going to something very like design heavy or like maybe like engineering or architectural heavy, you don't really use a lot of trig. Like to be completely honest with you. Uh, so like don't tell your math teacher I said that, but like just to be completely honest, you don't use trig very, very much. Okay. Cool. So I'm starting to see some answers coming in. For those of you guys that are putting in like square root 98, simplify your answers. That's just a good like habit to get into. Because if you put that in like a competition or like a math pro or like a math test or something, you probably won't get credit. So just always simplify your answers. A good thing to keep in mind. Okay, great. So I see a lot of people saying that 7 is the other leg and the hypotenuse is 7 root 2. 45, 45, 90 triangles are beautiful because there's literally only two possible side legs. If we know that one leg is 7, obviously the other leg has to be 7 because the legs are the same. And the hypotenuse is going to be just the square root of 2 times the leg. So 7 square root 2. And yeah, that's pretty simple because the ratio is 1 is to 1 is to square root 2. So pretty self-explanatory. All right. Yes, I can go slower. Okay, thank you guys. I really appreciate you guys like helping me with the pacing. I sometimes just lose track of myself, so thank you guys so much for like helping me pace myself. Okay, let's take a look at this next question. And maybe we'll actually have someone solve this. I feel like I've been doing a lot of the solving lately, so maybe like someone can help me out here. All right, when we think about this next question with the 30, 60, 90 triangle, and let me change colors too while I'm letting you guys think. Okay, I see one answer of 6 root 3. Uh, Indicate which leg that's for. Is that for your short leg or your long leg? Okay, I see 6 and 6 root 3. Okay, awesome, awesome. Yeah, so I'm seeing a lot of people saying the short one is 6 and the long one is 6 root 3. Does anyone want to like unmute and maybe answer for this one? Okay, yeah, I see Manit has his hand raised. Go ahead, Manit.
So for the short leg, you just have to divide 12 by 2, which equals 6. And for the long leg, you said you have to multiply it by square root of 3, which equals 6 square root of 3.
Yeah, perfect. So because the ratio is 1 is to square root 3 is to 2, if the hypotenuse is 12, that means you're multiplying this entire ratio by 6. So I have to multiply this thing by 6 to get the 12. For the short leg, that's represented by this 1 at the beginning. I have to multiply that by 6 to get the short leg of 6. And then finally, I just have to multiply the 6 by the square root of 3 to get the middle leg or the long leg. Yeah, the long leg or the middle side. All right, let me pause here. How do you guys feel about this? Is this good? Yeah. Okay, awesome. Let's do a couple of challenge problems. I feel like they're only challenged in the sense that like they're not exactly what we've been doing, like looking at hypotenuse and finding the other sides. But they are very, very similar in the sense that they still use these very important ratios. So let's take a look at this next question, and I will see if we can try to get a volunteer again. I think it's so much more fun when you guys teach each other and help each other out than just me like talking to you guys for an hour straight. I think that gets quite boring. Okay. Um, cool. So I see some people saying 10 for both legs because in this case the legs are the same. Cool. Any takers for this question? Anyone like just dying to speak, just dying to interrupt me? Okay, I see Manit's hand again. Manit, if no one else wants to go, I will see if I can call on you. But is there any other answers? A lot of you guys are putting stuff in chat, but if you want to share like vocally or verbally too, that would be really awesome. Okay, mic's not working. No worries at all. Awesome. There are no wrong answers here. So even if you're like, oh, I don't really know if how I did it is correct, um, just let me know. We would love to hear what you all have to say. Oh, awesome. Okay, Vishith has something to say. Let's hear it.
Oh, Um, so it says that the 10 then square root 2, so the formula was h equals to wait, where is it?
Yeah, no, you're doing really
Yeah,
great.
and then like the legs are gonna be 10.
Yeah. So we know the hypotenuse is going to be square root 2 times the legs. That's absolutely right. And from there, Bishop was very quickly able to determine what the legs are. So thank you so much for unmuting, sharing that. That was really, really awesome. Let's kind of recap what happened here, right? So we know in a 45, 45, 90 triangle, the ratio of the sides is 1 is to 1 is to square root 2. Now the square root 2 corresponds to the hypotenuse. We know the hypotenuse is 10 root 2, so because of that, we are multiplying this entire ratio by 10. And if I'm multiplying the entire ratio by 10, that means my legs are both going to be multiplied by 10 as well. So that's just 1 times 10 is equal to 10 for each of the legs. All right, how do you guys feel about that? Does that sound okay? Let me pause here because I know a couple people had questions before. So if you guys still have questions now, please do let me know. Okay, no questions. Awesome. Let's do one last question and then we can move on to maybe some more fascinating things. Oh, yeah. Awesome. So, for those of you guys asking about like how we got the answer, I think that was explained when we kind of looked at the ratio. A big thing to know about a lot of these questions is if you're just asked about like, oh, what's the legs or what's the hypotenuse in the special right triangle, all you have to do is look at the ratio of the sides. So in this case, with the 45, 45, 90 triangle, because because the hypotenuse is 10 times the square root of 2. Remember, the legs and the hypotenuse are in a 1 to square root 2 ratio. So if the hypotenuse is 10 times the square root of 2, that means the legs have to be 10 in order to keep up that ratio. So if you're kind of like, okay, how does this ratio stuff work? A good way to think about ratios is also fractions. So we can say that oh, leg over hypotenuse, which I'll write as HYP, is equal to 1 over square root 2 in a 45, 45, 90 triangle. So if I know the hypotenuse is 10 times the square root of 2, I can write that the leg divided by 10 square root 2 is equal to 1 divided by square root 2. So if I solve for this, I'll get that my leg is equal to 10. So hopefully that clears up like how this ratio stuff works. But I think once you understand like the side ratios in a right triangle for a 45, 45, 90 triangle, it will be much clearer. It is very clear how to get from there to there. Okay, awesome. And I already see so many people putting in answers for this next challenge question. So does anyone want to share how they got their answer? I think a lot of people are like in agreement. Okay, aside from me, maybe. Okay, yeah, Monique, go ahead.
So since the long leg's 4 but times the square root of 3, you can just divide it by the square root of 3 to find the short leg, which is 4. And then you can multiply it by 2 to find the hypotenuse, which is 8.
Yeah, perfect. So like Manit says, I can kind of look at where these ratios are coming from. So I know that the short and long leg are related by a factor of square root of 3. So if my long leg is 4 over root of 3, that means my short leg has to be 4 in order to satisfy this ratio. And I know that my hypotenuse is going to be double of my short leg. So if my short leg is 4, then my hypotenuse has to be 8. So this is my short leg, and this is my hypotenuse, and that's how we find the rest of the sides in this 30, 60, 90 triangle. Okay, I'm gonna pause here because this kind of like is the end of our section on special right triangles. How do we feel about this? Is this like okay? All right, I hear no questions, so let us go ahead and take a look at the next section. So, oh, this is new to you, Nahal. That is totally cool. If this is like tricky or there's something weird, feel free to stick around after class and we can talk about it. Okay, awesome. Ariz is getting to understand it as well, which is great. Yeah, this is definitely like high school material. So if it's challenging, that's okay. That should be challenging. It should be challenging. But yeah, If you guys like need more than what's like what I'm explaining in class, that's totally cool. Um, just make sure to stick around and we can answer it. But yeah, like Anika says, y'all are all doing really great. Really great like participation and stuff, which I think is awesome. So yeah, you guys are doing really wonderful. Okay, let's go ahead and take a look. So earlier today, when we were talking about looking at the 30, 60, 90 triangle, I brought up an equilateral triangle. And luckily enough, today we are also going to look at the equilateral triangle. Um, I think like in the realm of triangles, there's very few like special ones because there's very few ones that have like nice angles to look at and also nice sides to look at. So the special right triangles are a very, very niche group. But you also have equilateral triangles, which are extra special. So an equilateral triangle, which I think you guys all know, has equal sides and equal angles. So let's just draw one again, just cause. I feel like I've used a lot of green. Let me use like an orange. Okay, cool. Yeah. Okay, here's my equilateral triangle. Yeah, so as you can see, this is my attempt at drawing something where the, let's make this bigger. Okay. The sides are all equal, which we kind of denote with like a line kind of just going through it. And the angles are also equal, which we also happen to note with a line going through it. So this is, oh, that was a really bad angle mark. Okay, so this is some important geometry notation. If you see a line on a side, look for another line going through that side because that shows that the sides are equal. If I had instead had two lines, like here, this would mean that there's another pair that this side is equal to, but it's not these sides that only have one mark. So every time we see congruent sides, we'll just add an extra dash. And then for the same reason, we'll also do angles throughout or we'll do like lines throughout the angle marks. Okay, so just a little bit of notation. If that's a little weird to you guys, let me know and we can talk about that, or I can clarify a little bit. Okay, so aside from the fact that their sides are all the same and like you can very easily calculate their perimeter, the other important thing we like to find out about 2D shapes in general is their area. So let's go ahead and kind of see if we can derive the area formula for an equilateral triangle. And for this, we're going to revisit the very handy-dandy perpendicular that I dropped earlier. So the perpendicular, also known as the altitude in this case, is going to go right down the center of the equilateral triangle and intersect this horizontal side at a 90-degree angle. That's what makes it an altitude. It's at 90 degrees. And the reason why we like altitudes, or why we like 90 degrees a lot, is because the area of a triangle in general happens to be 1/2 of the base times the height. And the reason why that is if you look at any triangle, you can construct a rectangle from it just by doubling that triangle along one of its sides. And it's very obvious to see in right triangles. It might be a little harder to see in something that maybe looks like this. You might be like, okay, where's the rectangle in here? So I encourage you guys, play around with different triangles, like maybe obtuse things or maybe acute things, and see if you can show why this formula is always true. But this is really important to understand for triangles, comes up all the time, so very important. But in this case, we have an equilateral triangle, and I don't see any right angles yet. That's why we drop this perpendicular altitude to get the right angle. Hold on, I should actually note only for right angles. Well, technically, okay, never mind. I lied. Technically, I lied. Because you can find the height of any triangle. Great. Okay, yeah, that is not only for right triangles. I like slipped up for a moment there. That is my bad. Okay. Yeah, it is for all triangles. Thanks, Minutes. Okay. I was like, I don't even know what was happening to me. Okay. Let's take a look. So I'm going to go ahead and instead of giving like maybe a numerical value for the side this time, I'm going to go ahead and define a variable. Now, because I don't want to deal with fractions again, actually it's okay. Let's deal with fractions. I'm just going to make you guys suffer. I'm kidding. Okay, so we'll say each side has a length of s. Now we talked about before when I dropped this perpendicular, it would divide the side in half. The reason exactly why that is because these two triangles are congruent. meaning all their sides are the same and all their angles are also the same. I promise you guys, this is like not super torturous. It's actually very interesting. Yeah, okay. I was just kidding. Okay, so if we look here, technically, like, okay, actually, sometimes congruence things can get very, very complex to show that two things are actually the exact same. But we got very lucky. We have a lot of information given to us. So we can conclude that this triangle over here and this triangle over here are the exact same. And maybe I should start putting some points, some labels. I'll say this is A, B, C, and this is D. So I'm going to say that A, B, D is congruent to B, oh wait, I have to be very careful with how I do this. C, B, D. Okay, so a couple things to note here, and we'll go a lot more in depth in this kind of notation and the symbolism and what's even happening here in a future class, but I do want to introduce it. This is what we call a congruence. And if you don't know what congruence means, all it means is same. They are the exact same. Like you literally take a copy machine, you run one triangle through it, and you get the exact same triangle. It's not, the sides are the same, the angles are the same. There is literally zero difference. You could not find the difference. Oh yeah, I can make it a little darker. And actually, I think thickness will help. Okay, yeah, let me use like a bright red or something. Okay, anyways, going back to this, a couple things. So this symbol over here means congruent. Okay, that means they are the same. And you might have noticed before that I was like, wait, I need to make sure I get these vertices the right way. That is because when we are listing congruent triangles, our vertices have to be in the right order. Otherwise, you're not necessarily describing the appropriate triangle. So if this went like totally over your head, that's okay. I just wanted to introduce this. We will probably spend like multiple lessons talking about this kind of thing. So it's okay if you're like, okay, I'm so lost. The important thing is equilateral triangles. So let's return to that. We know now that these are congruent. We can see that these angles are the same. We can also see that these angles are the same and these angles are the same. But also, we know that this side is the same as this side. And we know that obviously BD is common to both. So we know that these two triangles are the exact same. And because of that, we know that AD and DC are equal. What do you guys think about that? Like, are you like convinced 100% that AD and DC are equal? Okay, Vineet says yes. Sai says he is very lost, which is okay. If you are lost about this congruent stuff, don't worry about it. What matters is, do you understand this equilateral triangle stuff? Yeah, it's like a bisector. That's a good way to put it. So a bisector is going to divide this in half. Excellent. Okay, I think we're on the same page here. So a lot of you guys are convinced these two are the exact same. That's good. Um, Now, because they're the exact same and the total length is S, we know that AD is S over 2 and DC, oh, that looks kind of weird. And DC is also S over 2. They have to be the same in order to add up to the total length of S. So based on this, can you guys tell me what BD is? What is the length of BD? Think about what we know about this kind of relationships here. We know that ABD is a 30, 60, 90 triangle. So think about how we can use that. Okay, I see. Yeah, there we go. Yeah, so it's going to be S times the square root of 3 over 2. That's because AD is the shortest side. It's opposite the 30-degree angle. So if AD is S over root of 2, the long leg is going to be square root 3 times of that. So very simple. It's just going to be S over 2 times the square root of 3, which is shown here. Amazing. So let's go ahead and see how we can find the area of this total equilateral triangle. I know my base is going to be S. Okay, and my height is going to be S times the square root of 3 over 2. The height always has to be perpendicular to the base. There are no exceptions to this rule. It must always make a 90-degree angle. Now, where that angle occurs is going to be different depending on the triangle. So a little bit of foreshadowing for you. Okay, so we can say that the area is going to be equal to 1/2. The base in this case is just length S, and the height is going to be S times the square root of 3 divided by 2. So this is going to be S squared times the square root of 3 divided by 4. And that is the area of an equilateral triangle with full proof. All right, let's pause here because we did a lot of stuff. How do you guys feel about this? Does this sound okay? Like, does the proof make sense? If you are lost, where did I lose you? Take a second to digest and let me know any questions you have. Okay, Arav says good, and then Aris says not good, which is okay. This is a lot. Like, this is totally a lot. So we can definitely run through this again, but let's see how everyone else is feeling. So let me know if you're okay or like not okay or like what is happening. Okay, not good. Okay, that's okay. That's okay. Yeah, we can totally recap. All right. Cool. So let's do a little recap. I think it's worth reviewing. Now, how else are there review classes? We don't really do a lot of like review stuff, but if you want to ever discuss like homework or class material, you can always stay after class, or you can always shoot me an email and we can discuss like that. Awesome sauce. All right. Um, cool. All right. Let's look at another maybe a different perspective to look at this. Maybe a different perspective. So I'm gonna make this a little smaller and I'm gonna give you guys a nicer pre-generated diagram that maybe is a little easier to digest than my hand-drawn one. Okay, so this is our triangle. This is an equilateral triangle. The vertices are a little different from how I had them labeled, but you can notice how the sides are the exact same. So we chose the length of each side of the equilateral triangle to be S. Let's break this down. So I'm going to draw a perpendicular because I need to find a height. I need to find the length of my altitude. Why do I need to do that? Because in order to find the area of a triangle, I need to find the base and the height. The area of a triangle is going to be 1/2 of the base multiplied by the height. So let's say my base is BC over here. That's going to be a total length of S. If I want to find that height, I need to drop a perpendicular, something that makes a right angle with that side. So I draw a line from A and I make sure that it lands exactly 90 degrees to BC. That's how I get this right angle at D. How do we feel about that? Do we understand why we need to even draw this line, this altitude as we call it? Okay, I see a couple of goods. Awesome, awesome. All right. Okay, so now that we've understood where this is coming from, let's break down how we get some of these side lengths. So when we talked earlier about like the 30, 60, 90 triangle, we kind of already like foreshadowed this, but I will explain once again why this is true. So we know that ABD and ACD are the exact same triangles. They have the exact same angles, both are 30, 60, 90 triangles, but they also have the exact same sides. We can see that because they both have a side length of S. Our hypotenuse specifically is both length S, and their longer leg is both length H. So I have plenty of information to conclude that this is two perfectly equal triangles, 30, 60, 90 triangles in particular. How do we feel about like getting to that fact? Do we feel confident that this is like these are two triangles that are the exact same? Okay, okay. I see people saying yes. Awesome. So now that we know that these are the exact same, we know that BD and DC have to be equal. They're sides that are corresponding, so that means that they have to be the exact same lengths as each other if the triangles are congruent. So if they're the exact same lengths, that means each one has to be half of S, or S divided by 2. So BD is S over 2, and DC is S over 2. So now I know what my short leg is. I also happen to know what my hypotenuse is, so I can very easily find my height. I know in the 30, 60, 90 triangle, my height is going to be the square root 3 multiplied by the shortest leg. So the h is going to be S root 3 over 2. All right, and if you're not convinced that like, oh, maybe this is not half of it, we actually already know the side length S in this 30, 60, 90 triangle. So that is another way I can find what H is. Both ways give you the exact same result for H. So pretty important to understand. Okay, cool. I don't see any questions, so let's go ahead and move on. So now we have all the information we need to calculate the area. We have the height that is going to be perpendicular to the base. So I can go ahead and plug both my variables into this equation. So my area is going to be 1/2 times the base, which we said is BC, or length S, times the height, which is going to be the line that is perpendicular to BC. And that has length S √3/2. So if I go ahead and multiply this all out, I will get S squared times the square root of 3 divided by 4. And that, once again, is how we get our area of an equilateral triangle. Alrighty. Does this make a little bit more sense? Do we feel a little bit more found with this question? Do we kind of understand where we're going? Yeah, okay, that's really great. I'm really glad. I think if you are still, so the main idea here is kind of looking at the proof and seeing how we can use 30, 60, 90 triangles in action. So this is definitely review this proof, and you will be using this idea, this formula quite a bit. So we want to make sure to understand where it comes from and to be familiar with it. Okay, let's see. What kind of problems do I want you guys to do now? Hmm. Okay, let's just practice a couple of area problems since we're almost done. And then we'll like kind of do like a cool down and just return to some old ratio problems. So that's a little like so you end on a nice note on something that you're very good at. All right. So can you guys find the area of a triangle with side length 4? I'll avoid the messy fractions for you. So area of equilateral triangle with side length 4. Wow. As soon as I finished writing the question, so many people already had answers, which is super speedy quick. Yeah, I'll give you guys a couple more seconds just to think about that. Perfect. Yeah, it's 4 times the square root of 3. Very good. And all you have to do is just use this formula that we've identified up here. So if the side length is 4, we will just plug this in. S is 4, so that gives us 16 times the square root of 3 divided by 4, which very easily simplifies to 4 square root of 3. So just a quick application of how we can very quickly find the area of an equilateral triangle. Equilateral triangles are special because they make up a lot of different shapes, and not just 2D shapes, also 3D shapes. So it's very important to understand their properties and all kinds of things about them. So this is one of the most important ones. Yeah, let's do another one. Maybe I'll make this one like a little messier. So instead of side length 4, let's do a side length of 5. Yeah, actually, I think this will be our last question instead. But you guys are good at this, so this will be like a nice happy note to end on as well. All right, so just to clarify, go ahead and find the area of an equilateral triangle with side length 5. All right, I'm starting to get a couple answers, but I'll wait and give everyone a little more time. Okay, yeah, I'm starting to see that everyone has put in 25 times the square root of 3 divided by 4, which I have to say is 100% correct. What an awesome way to end off this class. Let's explain how we got that. We know that the side length is 5, meaning that we can plug in S is equal to 5. So the area is going to be 5 squared, or 25 times the square root of 3 divided by 4. There's not even much for me to write because we've already done the big step, and all that's left is plugging into the equation. Okay, so we have totally covered a lot today, and a lot of this is very advanced stuff. So if you're feeling a little overwhelmed or confused, please don't hesitate to like stick around or ask a question or shoot me an email. A big part of this is a lot of what I spent today was like deriving different formulas and proofs and things. So I think it's important that you guys understand where all this stuff comes from. So even if you're like, oh man, this formula is super simple, but I don't know where it comes from, rewatch our recordings and learn where it comes from because that's really important. Um, The problems are easy themselves, but the ideas behind them are definitely complex. So yeah, if you guys do have questions, feel free to let me know. Otherwise, you guys are free to go. Thank you so much for joining me tonight. I had a wonderful time. I hope you did too. And I look forward to seeing everyone next class. All right. Thanks, everyone. Bye. Bye, Bashit. Bye, Sai Praneeth. Bye, Maneet. Yeah, thank you all so much. Awesome. Bye, Zia. Bye, Invika. Bye, Nahal. Bye, Rob. Thank you. Bye, Ariz. Awesome. All right. For those of y'all left, if you guys have questions, feel free to like raise your hand or like let me know. Amari asked if I could, can I come early to pick the next icebreaker? Absolutely. Yeah. I always need new icebreaker ideas. So if you want to help out next time, that'd be awesome. I'll try to open the Zoom like maybe 5 minutes early. Awesome. Thanks so much, Amari. Yeah. Bye. Awesome, awesome. Okay, I don't see any questions from anyone else, so I'm gonna go ahead and close the Zoom. Thank you all so much and have a great night. Oh, yeah, Tanish, did you have a question? Yes, what's up? Oh, you guys can call me Sam. Feel free to call me Sam. I'm like barely 5 years older than y'all. Awesome. Yeah.